The share of wind and solar, and by that generators with power electronic converters, are steadily increasing in the grid. There is a consent in the industry that there is a need for advanced controls in order to reach the desired decarbonization goals. Offshore wind farms are not the only application area for wind turbines with grid forming capabilities. The expected benefits for the onshore applications might be even higher, and the results of promotion projects are easily transferred to such application areas. Build-up supply chain is not the only R&D of new technical features. Equally important is the certification of the wind turbine generators. And for this, a clear set of requirements is needed. Work in promotion provides the foundation for such requirement specifications. Before market introduction, the actual ancillary service product needs to be qualified. For example, as we speak, generators using power electronic converters are not qualified for all ancillary services in Ireland, which has one of the world's most developed ancillary service markets. This preparation task is on transmission system operators and needs to be addressed soon to create sufficient confidence for wind farm owners. For the required massive integration of offshore wind, new concepts are needed. We at Hitachi ABB Power Grids are therefore developing solutions for hybrid interconnectors. Those are HVDC interconnectors in between the countries that also collect the wind energy along the route of the cable. For the future, it is important to know how the optimal combination of offshore wind farms with grid forming capabilities with such hybrid interconnectors should look like in order to maximize the stability of the complete power system. The type of the wind turbine generator is not known when designing the offshore wind connection system. Assumptions for expected generator performance are important for the design process. For the state-of-the-art wind turbine generators, requirements and benchmark performance are described in grid codes and validated by turbine certification. New technical features, though, such as grid forming capabilities, are difficult to assess early on. The results of the promotion project provide a starting point for the development of requirements and benchmark performance, and by this de-risks the design process for offshore wind connection systems.
Hello everybody, I am Lorenzo from Ørsted Wind Power in Denmark, and I'm gonna give a small contribution to this conference by explaining how a wind farm developer like us see the results of promotion being relevant for the industry in the near and longer term future. As I said, I'm Lorenzo from Ørsted Wind Power in Denmark. You can see my contact details here. My experience comes from a PhD project in the VSC HVDC connection of offshore wind farms, and then I've been involved vastly with electrical design and grid compliance processes for large offshore wind farms, mainly in the UK and the US. I have also an interest in the application of HVDC to offshore wind development. In promotion, I've been the main contact from Ørsted, and I've been involved in work packages 1, 3, 11, and 16, and also with a small role in the special project in work package 12, where we've looked at the feasibility of the Bornholm energy island concept. In the context of this presentation, I'm going to give an answer from the wind farm developer angle to a few questions that were raised on the work done in work package 3 that was led by DTU. The first question is, how would you characterize work package 3's contribution to the de-risking of wind turbines grid forming control, and how relevant they are for the industry? Well, we think that work package 3 has contributed significantly to raising the confidence in the feasibility of wind turbines with grid forming control capabilities, because grid forming controls based on different schemes have been tested in this work package under a variety of scenarios. And also we have seen that some tests based on real-life black start scenario were performed. This, of course, increases the confidence level and shows that the grid forming capability is something that can be relied upon quite safely in the future. And the application of this feature is actually quite vast, and it can go from grid forming capabilities being applied to weak grid conditions, and also as a means to improve grid stability in general, and to offer different power system services such as black start. The next step, which is not necessarily a minor one, will be for the industry to implement the controllers in commercial wind turbines and to devise the necessary deployment plan for this functionality. Question 2 was, what are the necessary next steps towards commercialization of offshore wind power plants with grid forming capabilities, and what is the role of the industry in this? Yeah, I think that integration of grid forming controllers into commercially available turbines will be a task mainly for the wind turbine manufacturers, some of which have already done demonstration tests to some extent. On the one hand, we see that a necessary thing for this to be deployed is the demand from the customer side or grid code requirements that need to be there. And in this context, the need for grid forming capability could be triggered, for example, by low short circuit ratios, so like weak grid conditions, or supply of backfeed power to various parts of the wind farms, or the black start service to be offered to the system operators. And furthermore, we could even argue that the grid forming converters may be a more cost-efficient solution compared to, for example, more conventional ones based on synchronous condensers to achieve system stability with very large penetration of inverter-based renewable energy sources in the power system. However, on the other hand, the supply chain must be ready for the implementation with the right level of confidence that the necessary modifications to the turbine controllers are acceptable for the product design, and also with a proper timeline in place for implementation and testing of this new functionality. The third and final question was whether islanded operation based on the grid forming controls developed in work package 3 is an important aspect for the industry, and if yes, what are the main areas of applicability? Among those could be household consumption during transmission outages, increased reliability of energy islands, or anything else. As a wind farm developer, we actually think that islanded operation can depending on the cost of the grid forming functionality, be a very first possible application of these controllers. The potential savings both for the developer and for the environment are tangible, and the risk of employing a new functionality is probably more manageable when the turbines are not required to black start a reasonably large portion of the power system, but their action is more localized. So we believe that the proof of concept of the functionality could probably be a staged process, starting from turbine house load coverage, and then continuing with energization and power up of the collector grid and offshore substations, for example, and then eventually continuing towards the onshore substation and the connection point, and finally to a proper blackout operation.
Very much for promotion WP3, the invitation for Equinor share its perspective as an offshore wind farm developer. My name is Wei He. I work at Energy Storage and Emerging Technology at Equinor. And Equinor's promotion team, technical team, Camera, and I think everyone knows him. He doesn't need any introduction. He is the leading engineer at research and the project department at Equinor. Wei He, it's me, and we have two experts from electrical department at Equinor. That's Dr. Francesco Mara. He has worked for the work package 4, and Dr. Nicola Chesi. He worked for work package 11. Our legal representative, Lena Mittet, and the financial form signing, Beyond Written. Equinor has tasks in 7 work packages, work package 1, 3, 4, 8, 9, 11, and 12. Now we'll come to work package 3, wind turbine generator, convert interactions. Work package 3, dream team, led by Professor Nicholas Coutulis at DTU. And the dream team consists of 4 leading universities. So they are DTU, University of Valencia, University of Strathclyde, RWH Aachen University, and 8 industry partners are EnergyNet, ABB, Siemens, MHI Vestas Offshore Wind, FGH, DNVGL. It was also very interesting to work together with Ørsted, and they are the offshore wind farm giants, and their offshore wind farm portfolio maybe 10 times larger than Equinor. So Equinor, the company, is 10 times larger than Ørsted. We have 25,000 colleagues, and while they have more than 2,000. And from work package 3, and after 4.5 years hard working, and there are 8 deliverables from the requirements, control strategies, and to the test procedures, evaluations, and even the recommendations for the future. And the 8 deliverables have shown that work package 3 has reached its 3 objectives: defining functional requirements of offshore wind farms, identifying general control strategies for both wind turbines and offshore wind farms, specifying evaluation procedures through simulations and tests. From Equinor's perspective, as an offshore wind farm developer, WP3 has significantly contributed to the de-risking of wind turbine grid forming control. increasing the confidence of meshed HVDC development, and reducing the operational risks. The WP3 Dream Team has initiated not only the collaborative research effort, but also the further commercialization potential. Promotion results are useful for many of Equinor's ongoing and future offshore wind farm projects, including Dogger Bank offshore wind farm, 3.6 gigawatts, 130 kilometers from the coast. Also, the offshore wind farm connections to Equinor's offshore oil and gas platforms. It extends promotions meshed HVDC grids and their connections to offshore loads. On behalf of Equinor's promotion team, I would like to thank you very much for this high-impact promotion project. Thank you very much for your attention.
My name is Tusitha Abeyasekera. I'm from Mitsubishi Vestas Offshore Wind in Denmark. I am a program specialist in the electrical area of the offshore wind turbines that we produced. So my experience is I'm having a PhD in electrical engineering from Newcastle University. My background covers high power electronics, control, and grid compliance. At MVOW, I'm responsible for the electrical product programs for offshore wind turbines, design and specification of high power converters, and offshore wind grid compliance. So regarding the work package 3 in the Horizon 2020 promotion project, I have been the main contact from MVOW and been very deeply involved in the work package 3, which touches upon the control of the conversion part of the wind turbine. So lately been contributing towards black start and grid forming control of the offshore wind turbine, also in the design of the control system for the grid forming offshore wind turbine, as well as requirement specifications and simulation validation. How would you characterize the work package 3 contribution to de-risking of wind turbine grid forming control, and how relevant they are for the industry? So answering this question, I think the initial step for grid forming control of offshore wind turbines have been made under the Horizon promotion project, specifically in the work package 3. We find it extremely useful and a very good, strong step in the right direction in the application of the control systems that are developed and requirement specifications and the validation techniques that have been developed in the work package 3. So if I may speak from a point of view of wind turbine manufacturer in the offshore wind area, Mitsubishi Vestas sees this step of initiating the foundation control system for grid farming control of offshore wind as a very strong step in the right direction and a very good step at the right time where the industry is now. We would see that we could identify 3 main benefits of the contribution done in the work package 3. One of the key and an obvious benefit is the black start support for onshore grids that we are expecting that is going to be required in the very near future. A second benefit is an expanded reach for offshore wind to integrate into weak grid areas that we also see is in the very near future is going to be useful. And a third point is the stable connection of large offshore wind resources to high power electronics penetrated grids. So these 3 points we have identified as a very strong contribution towards the industry from the Horizon 2020 promotion work package 3. What are the necessary next steps towards commercialization of offshore wind power plants with grid forming capabilities? What is the role of the industry? So again, if I may describe this in 3 steps, we believe the first next step towards commercialization of grid forming control for offshore wind plants would be the detailed functional requirements that needs to be formulated by working together with the transmission service operators, offshore wind developers, and wind turbine manufacturers. That being said, the next step would be to take those functional requirements, specifications, and get them implemented in a real-time digital simulation environment, also followed by validation of the same. And the third step would be to integrate these grid forming controls that have been developed and validated in simulation and real-time digital simulation environments into prototype turbines. And the third step also could be followed by the final step, which we believe is testing and verification of grid forming control of offshore wind plants in an offshore wind park context. Thank you.